Morning, guys. I want to talk about parametric modeling today. We're not going to have an assignment, but that doesn't mean that we can't talk about the things that we would normally be talking about in school. So I'd like you to sit through and watch this entire display, and then I'm going to create a parametric modeling exercise in Inventor so that you guys can get a load of what it actually looks like. So what is parametric modeling? We're going to go over the types of computer design parameters that are associated with it. We're going to review the geometric constraints that go along with it. Parametric constraints, what they are. The creation of parametric equations that maintain some geometric proportions that you can also use along with the functions that we started to use in Inventor when we did this earlier. 3D CAD programs use parameters to define a model of a design solution. Now what would that look like with our parts earlier? We did a width of 0.75. We may have done the height of 2 times 0.75, and we may have done the depth of 3 times 0.75 to create our puzzle parts. In 3D CAD programs, they use parameters in many different forms as well as those to determine how the system will behave. So I can say, rather than a height of 0.75 and a width of 2 times 0.75, I can say a height of 0.75 and a width that is 2 times the height. If we give those things dimensions 1, dimensions 2, dimensions 3 as names, so that we can refer to them as D1, D2, and D3. We've talked about some geometric constraints already. Geometric constraints such as parallel, perpendicular, concentric, tangent, things of this nature. Parametric constraints, we'll go into what that means now. And assembly constraints, we have kind of talked about with the mate and the flush type constraints when we started to assemble our puzzles. Non-numerical geometric relationships that users assign to sketch elements. Those are the ones that we talked about, like parallel, arcs being concentric or having the same center, and making a line horizontal. These are what some of those look like when you're using it. Doesn't matter whether it be in Inventor, Onshape, Unigraphics, SketchUp. These are some of the things. And if you look at it, you can see that the red line and the blue line are perpendicular. The red line and the blue line are parallel. The red circle and the blue line are tangent. These are very easy to kind of relate to, as to say. Parametric constraints are used to control the size and the location of the geometry. They may take the form of simple numeric values such as 2 inches or 25 degrees, or as we started to use, you can see that they can take the form of an abstract algebraic formula, such as the dimension 2, or D2, times dimension 0, divided by dimension 5. So those would be 3 pre-existing dimensions that are already there. The fact that it goes up to D5 leads me to believe that there are 5 dimensions, though. They can be tied to a spreadsheet that allows for more complex mathematical formulas. And to do that, we can upload that in the form of an Excel spreadsheet. Algebraic equations that use variables can be substituted for individual numeric values. Such here, D7 is equal to D2 times D0 divided by D5 and plus 2 inches. The resulting dimensional value may change, but the formula is always going to remain the same. Okay? the symbols that we use: add, subtract, multiply, divide. You can find all of these on your numeric pad. So what would we use this for? We could use this in the scenario that a child's proportions are similar to those of an adult, and a chair could be dimensioned in such a way that a change in the seat height could be scaled from all the other chair features uniformly. Or we could do this with the thought that the distance or the ratio from a belly button to a chin is one length. So as that grows, if we set all relationships to that and set D0 to be the distance between the belly button and the chin, and we measure that person, the distance from their belly button to their chin, and set that, we would have a perfect shaped chair for them, or a perfect size chair. Okay, so we can also do this with many different plates and many different machine factors, such as this, each dimension being a given designation, starting with D0. I'm not going to go through the rest of this PowerPoint just to show you how to make this plate, because this plate goes into a lot of details. I believe that it's easier to relate if I create another video with me actually doing it on Autodesk Inventor. That will be part 2 of this video. Okay guys, I'm back now to do a quick parametric model for you. I'm in Autodesk Inventor. I've already created a standard IPT, and I am now going to click my first sketch. I'm going to click on the front plane, and I'm going to add a circle. I'm just going to click and drag this circle and click on dimension. When I click on the dimension and click on that circle, you'll see it says edit dimension D0. Okay, that is the very first dimension that we're putting into this model. Notice it doesn't say D1, it says D0, so we can use D0 as a reference point. I'm going to set D0 to be 1. Finish this sketch, extrude this, and I'm going to set this to be D0 divided by 8. So what it's done for an extrusion is made that dimension the thickness of our first dimension divided by 8. I'm now going to put a sketch on the front of another circle. And I'm going to set that dimension to be lowercase d0 divided by 6. Finish that sketch. Turn this around, put another sketch on the other side. Put a circle here. Dimension this circle be a function of d0 divided by 2. Finish this sketch. Now, in order to do a subtraction between two unlike surfaces, I'm going to do what's called a loft. I'm going to click to add my sketch. I want to loft or subtract between sketch 2 and sketch 3 over here in the model browser bar. I'm going to click OK. Oops. And I have to choose to cut that. When I do that, you can see now that I have subtracted the material from my model between two different size circles. Alright, so what I want to do is add a little bit of color to this up here from the adjust so that you can see the difference here. Alright, I'm going to add a little more color to offset the difference to make it easy to see on this surface right here. Okay, so we can see that I have a basic shape of an object here, all right? Now we know that from watching me build this, that this is 1 inch in diameter. I'm going to come over here to my model browser, and I'm going to expand Extrusion 1 and edit this sketch. I want to edit this sketch from the size of this circle from 1 inch to 1, 10, 100, 1,000 inches. Click enter, finish my sketch. Bam, all I see is blue. But let's zoom out on this, all right? So I made this thing 1,000 inches now instead of 1 inch. You'll notice it doesn't look any different at all. Okay, so I went from 1 inches to 1,000 inches, and everything basically stays the same. It looks identical. Of course, it barely would fit in this room right now. But let's go back here and take another look here. Let's go back into the extrusion, expand this, edit sketch 1, edit sketch, changes from 1,000 inches. Let's try 0.01 inch. Let's just make this thing tiny. Bam, finish sketch. That's gone. I can't even see it now. But let's click zoom all. Okay. So now we've made it so small that our graphics card isn't recognizing. Oh, there we go. It caught up. Our graphics card caught up with us. This looks like the same thing. It still hasn't changed between 1,000 inches and 1/10 of 1 inch or 1/100th of 1 inch. So you can see that creating something with parametric constraints allows something to be the exact same. You're just changing the ratio in which it is set to be. I hope this has been somewhat helpful. I'm going to go into it a little more in depth with some other Autodesk, and I'm going to try some Onshape and some Fusion and some SketchUp videos too, in case you guys are playing with those at home. But at any rate, thanks for watching.